Hello and welcome back to Math Class in Session. The dot product of two geometric vectors. Well, we've multiplied vectors times scalars, and we know what happens there. Now we're going to start to multiply vectors times vectors. How do you multiply a directed line segment times a directed line segment? Well, that's what we'll do today. It's called the dot product because there's two ways to do it. One way, you end up getting a scalar. The other way is you end up getting a vector. Today we'll do the one that ends up getting a scalar. It's called a dot product. Geometric vectors are vectors not associated with a grid. The ones on the grid are called algebraic. The dot product is also referred to as the scalar product because this product is not a vector, but it's a real number. So a vector times a vector turns into a number. And by definition, that number is? Well, let's take a look at a couple of vectors here. If we arrange them tail to tail, there's an angle. And the definition of the dot product of these two vectors is length times cos. It's the length of the one times the length of the other times the cosine of the angle between them. And we always consider the smaller angle. There is a reflex angle here on the outside. It's the one that's between 0 and 180. So length times cos is how I remember that. Some facts about it. We care about the smaller of the two, not the reflex angle. If theta is acute, then this dot product is positive because lengths are positive, so length is positive times the cosine of an angle that's acute, that will be positive as well. I put this one in a box. If the angle between them is 90 degrees, so the two vectors are perpendicular, then length times cos will be 0 because the cos of 90 is 0. And I put it in a box because this comes up a lot. Two vectors are perpendicular, their dot product is 0. And if theta is obtuse, then the dot product is negative. The cast rule tells us that in the second quadrant, the cosine is negative. Moving, some properties. Well, most of the properties are intuitive and they are exactly the way you think it would be. For example, P dot Q equals Q dot P. It makes sense because this is length times cos, and this is also length times cos. So order of multiply doesn't matter. Order of dotting vectors doesn't matter. Distributive property, P dot Q plus R, the sum of a couple of vectors, is exactly the way you think it would be. We distribute the dotting, so to speak, over the bracket. Magnitudes property, I put this one in a box because this one's important. When we dot something with itself, we get the square of its magnitude. And the reason being, when we go length times cos, we're going length times length, which is length of p squared, and the cosine of 0 degrees, because that would be the angle between a vector and itself, the cosine of 0, we know from the curve, is 1. So this is just the square of its magnitude, dotting with itself. Associative property with a scalar. Well, k is a scalar, so a multiple of a dot product. This one's obvious. But it's maybe not obvious that we could also put the k times q. So we could multiply the q times that scalar and still go length times cos. So it's associative because we can move this factor, the scalar factor, in and around. Okay, let's do an example. couple of vectors, v and w, have an angle between them, 135, and the vectors have lengths, 4 and 7, respectively. Calculate their dot product. Well, we arrange them tail to tail. It's not the same as head to tail. Arranged properly, they look like this because of these words right here, between them. So this is the angle between them when they're tail to tail. And V's got a length of 4 and W's got a length of 7. So it's length times cos. Now, of course, I like the root signs. I like exactness. You could do this on a calculator and turn it into a decimal. That's almost as good. However, this multiply top and bottom by root 2, and you've got a 2 on the bottom dividing the 28 to a 14, and the root 2 is on the top now. Given that the vector has a length of root 5, calculate dotting it with itself. Well, it'll be the square of the magnitude. So the square of root 5 is the number 5. Suppose we dotted I with itself. Well, we'll get the square of the magnitude. And the magnitude of I is 1 because it's that standard basis vector, 1, 0. And so when we square that, we get the square of the magnitude. Suppose we dotted I with j. Well, I and j are perpendicular. So when vectors are perpendicular, their dot product is 0. And another example. Given that these two vectors, a plus 5b and 3a minus b, are perpendicular, and we are also given that length of a is twice the length of b, determine the angle between the vectors a and b. Now one would think, how are you ever going to do that? Well, the thing is, this word perpendicular gives us an equation. So if they are perpendicular, their dot product must be 0. So let's dot them to 0 then. And we have an equation. And now, using the distributive property. I like saying distributive property. I don't like saying FOIL, but that's probably a personal thing. FOIL them out. So it's 3a dot a, etc. 3a dot a minus a dot b plus 15 a dot b minus 5b dot b. And the middle two terms collect. And we're after an angle, so we would like to inject some trig in here so we can get an angle. So a dot b is length times cos. And we're also given that length of a is 2 times length of b, so every time I see a length of a, I'm going to write it as 2 times length of b. And so this will be 2 times length of b squared. That right there, that length of a is 2 times length of b, and everything else is the same. And so, now I take a big step here. 2 squared is 4. 4 times 3 is 12, minus 5 length of b squared. So it'll be so this will be 12 minus 5. That turns into 7 length of b squared. And this turns into 28 length of b squared cos theta. I just dragged it across the equal sign up here. Let's review what happened. 2 squared is 4 times 3 is 12, minus 5 length of b squareds. That's 7 length of b squareds. And this is 28 length of b squareds times cos theta. And I dragged it across the equal sign. The length of b squareds now cancel away. And like magic, we have cos theta equals negative 7 over 28. Which is negative 1/4. So therefore, theta is the inverse cosine of negative 1/4. Calculator tells us 104.5 degrees. And we found the angle between A and B, given this. Solving problems using a dot product. Let's go one more time. Suppose that the magnitude of a sum of vectors is equal to the magnitude of the difference of those vectors. Think about that. If you add them up, you get a certain sum, the magnitude of that sum. And if you subtract them, you also get the same magnitude. Prove that the non-zero vectors x and y must be perpendicular. I see the word perpendicular here. Okay, proof. Well, sometimes you start with what you're given. And we're given this fact. Let's start with it. Now, we're kind of stuck. I don't see any dot products. Something about perpendicular. Huh. Well, what you can do is you can inject a dot product into this by saying if I square magnitudes, I know that I'm dotting with itself. So we could square both sides. Now it looks like this, and this is the square of a magnitude, which we know is the result of dotting with itself. And so we can turn these into dot x plus y with itself. And now I've got the dot product injected into this given information. And now using the distributive property, this is going to be very much like squaring a binomial here. So it'll be x dot x, it'll be 2 times x dot y, and so on. So x dot x plus 2 times x dot y plus y dot y, and we're squaring a binomial. And here we are doing it again, x dot x minus 2 times x dot y plus, because of negative times a negative, plus y dot y. Examine our new equation, and we see that there's an x dot x on the left and there's an x dot x on the right, so they offset each other. There's a y dot y on the left of the equal sign, and there's a y dot y on the right, and so they offset each other. And if we took this minus 2x dot y and dragged it across here, we would have 4x dot y equals, well, there's nothing left on the right. And this means that x dot y equals 0. And if x dot y equals 0, we can conclude, therefore, that x and y must be perpendicular. Dot product of two vectors. You get a scalar. And that scalar is length times cos. Enjoy.